Hello, and welcome to the session on managing automated build processes efficiently. I'm Shawn Prestridge, and I'm the U.S. Field Applications Engineering Manager for IAR Systems, and I'm going to be your guide through this session. I want to thank you for taking a little bit of time. Automated build processes are becoming more the norm in embedded systems, and we wanted to address how you could actually do this within our IAR embedded Workbench product. So my agenda for this talk is to just give you a quick overview of who IAR Systems is, and then talk about continuous integration, what it means, how some people are using this these days, and indeed with Docker, Jenkins, and a few other things that are available. And then we're going to continue on to talk about the build tools for Linux that we've created, and we'll discuss how you invoke these from the command line. We'll also talk about code analysis from the command line, and then we'll talk about how you can move from the Windows-based embedded Workbench into continuous integration. And you can do that continuous integration both from the Windows side and the embedded Workbench for ARM, as well as the Linux side, which is our BXARM product, or the build tools for ARM. We'll also talk briefly about alternative builds with CMake and Ninja. I'll have some screenshots to show you some things, but I'm also going to try to do a screen share and let you take a look at what this looks like live so you can get a better feel for what happens when we do this. So let's just continue on. So IAR Systems is the world's oldest embedded C compiler company. We started in 1983 and we've been around for quite some time. We support over 14,000 different devices with our tools, and we have over 150,000 paying users worldwide. So there's quite a number of people that use our products, and we like to say that at least 30 times a day you touch a product that has had code that's been developed with the embedded Workbench. And we have an entire panoply of product offerings, not just the embedded Workbench, that can help you with functional safety requirements, code quality, security. So we have everything built around the embedded Workbench being the center of that hub. And to that end, most people these days are doing continuous integration, which means that as they're creating their code, basically things are continuing to be built out automatically by a system. So it's a series of automated build and testing systems that every time a team member commits a change to the code, what it does is it runs through a battery of automated tests in order to make sure that that code complies with the specifications and all the tests that the quality assurance engineers have put together. So some of the different continuous integration tools that we see customers using, Jenkins is a really huge one. Most of these on this list are going to be open source. Azure DevOps, Atlassian Bamboo, as well as Bitbucket, TeamCity, GitHub, et cetera, et cetera. So there's a litany of different ones. Everybody has their personal favorite. I'd say Jenkins and probably GitHub are some of the bigger ones that we typically see. But the point is that continuous integration tools try to be agnostic as to what the underlying compiler tool chain is. And the way that they do that is that they rely on that tool chain to be able to be invoked from the command line. So that means that as long as you can call that tool chain from the command line, then it doesn't really care what that tool chain is and how it's getting information back out. So that's how we leverage continuous integration and how other tools do it as well. Another really popular tool that we didn't mention on the last slide is Docker. So Docker provides what they call containers, and a container, if you're not familiar with that term, is very similar to a virtual machine, but it is a very lightweight, stripped down virtual machine. which means that it uses much less resources, and it should, at least in theory, run much, much faster than a virtual machine. So the idea is that containers are completely isolated from one another, so they're kind of like a sandbox. And when you operate inside of this sandbox, it means that one container cannot pollute the environment of another container. One common reason that people say they like to use these containerized builds is that they want to have a hermetically sealed build environment. In other words, one where they can absolutely recreate the build that they were doing when they shipped it out to production. And if there are subtle changes to the environment, depending upon what compiler tools you're using, there might be some artifacts that show up in the final binary where it makes it hard or possibly even impossible to recreate that build fully. So Docker was created in order to try to minimize that risk and to be able to fully recreate. So the Docker container, or containers in general, they keep the OS kernel and they keep copies of the application that you're going to be using for building inside of the container, so that whenever that container spins up, it's going to be using its own local copy. And anytime you shut down that container, it basically goes back to its base state to be able to preserve that that case where you're always building from the same spot. So it's exactly the same every time you start it up, so you get a pristine build environment every time that container spins up. Now, to this end, we have ported our tools over to Linux, the build tool chain. So we have a complete command line build tool chain that you can use from a Linux host. So that would be a compiler, a linker, an assembler, etc. The IARBuild utility allows you to basically call IARBuild with a project name and then with the build configuration, and it will build everything automatically. The Linux kernel on which you need to be operating has to be a 64-bit kernel. We've tested it on Ubuntu 18.04, so it should work on that version and later. And I've also kind of personally done a little bit of poking around on different Debian distros and a couple of other distributions, and it seems to work very well. But these are the ones that we've extensively tested it on. We distribute this in a Debian package format, so that makes it very easy for you to install it on your Linux kernel, as well as to be able to use it. And the folder structure mirrors the underlying folder structure on the Windows-based embedded Workbench for ARM. So that makes it much easier to find different things, and it means that you're not going to run into any problems where things aren't in the same folder position when you're looking for semiconductor company specific files, such as header files, flash loaders, etc., etc. It's all going to be in the same relative path position as it is in the embedded Workbench for ARM on a Windows-based system. As I mentioned, it includes all the device files. You get documentation as well as complete support for the 32-bit ARM toolchain at this point. So the way you invoke our command line tools, well, actually there's a number of different tools. If you look inside of the installation folder under ARM bin, you have tools like ICC ARM, which is the IARC compiler for ARM. You have IASM ARM, which is the IAR assembler for ARM. iLink ARM, iArchive ARM, which can help you to build libraries. There's the icstat tool, which is the code analysis tool that I mentioned previously. So cstat, and I'll talk about this in just a second, but it is our static analysis tool that can help you up your code quality game. If you look in a slightly different folder under the install folder common bin, there is the IARBuild executable, which allows you to basically call just IARBuild with the project name and the build configuration, and then it invokes the appropriate calls to all the other tools, ICC ARM, iLink ARM, etc., etc. So that makes it very easy for you to be able to use the tools. So as I mentioned, IARBuild uses a project file as its primary input. It also supports parallel computing if you'd like, because if you use all the cores on your machine, it's obviously going to be much, much faster at compiling different projects. It also supports multiple build configurations. So those configurations you can set up within the embedded Workbench. You can have as many different build configurations as you want. They talk about debug and release here. Some common things that we see customers doing is they'll also have a separate build configuration for automated testing, where they perhaps have some hooks for automated testing, or they're calling different macro functions to be able to get data off of the device while they're testing, or perhaps put the next test case in. So you can create as many different build configurations as you'd like. So the syntax, as you see from the screenshot, is IARBuild, then the project file name, then any configuration or any options you have, then the configuration, and then you can also have extra options beyond that, which we'll talk about here in just a second. So I mentioned the CStat static code analysis. This is going to include MISRA C 2004 and 2012 rule sets, as well as MISRA C++ 2008. Additionally, it has about 250 checks that come from the Common Weakness Enumeration from MITRE.org, as well as Cert C and Cert C++ coding standards. So that makes it incredibly easy for you to up your code quality game when you can check your code against this many static rules. Some of the more popular rules that we have, in addition to the standard checks that come from the CWE and Cert C, are the security checks, which come from Cert C. And those security checks are some of the more common ways that hackers try to break into systems, such as buffer overflows, which is also called stack smashing, data injection methods, null pointers. So we can check your code for those types of vulnerabilities to make sure that your code is of the highest possible quality, even before you run it on live hardware. Now, this is fully integrated in the Windows-based embedded Workbench for ARM, but even in the build tools for BXARM, you can still invoke CStat and have it do the static analysis, where you can very quickly and easily be able to find out what's going on inside of your code. Because what CStat produces by default is a SQLite database, and that SQLite database can be queried in order to find out, what rules did I check, what issues did you find, what files did you find it in, et cetera, et cetera. But it can also produce a nice little HTML format as well that makes it a little bit easier for you to be able to have a human readable format for that. So there's lots of ways that you can invoke that tool. CStat can be run from the command line. The easiest way to actually run it is by using IARBuild. So the syntax for that is you call IARBuild with your project file name, and then the -CStat_analyze, and then the build configuration, and then optionally other things that you may want to do, like parallelizing that. The CStat settings are stored in the project.ewt file, and the results, as I mentioned, go into that SQLite database, but you can also produce an HTML output as well, which makes life a little bit easier. I mentioned Docker a little bit earlier. You can actually run the tools from within a containerized Docker implementation, and we have this really cool GitLab or GitHub page that tells you how to run Docker. It has a complete tutorial about how to set up the Docker container with the BX tools for ARM. I will tell you that the tutorial is set up for someone who is running a complete Linux host, but I personally like to run mine on the Windows subsystem for Linux. Some of you may be aware that Windows 10 now has a Linux kernel inside of it as well, so you can actually run full-blown Linux stuff inside of Windows 10. So I personally like to use BXARM in my Windows subsystem for Linux, so I can just fire up a Linux shell and make it work. And BXARM works great for that. If you want to use the Windows subsystem for Linux, the only thing that you're missing from that tutorial that we have there is that you also need to install the Docker desktop that's available from the Docker webpage, and then it just works because the Docker desktop hooks into the Windows subsystem for Linux, and everything is good from that point. So it's pretty cool. But you create your own containerized image. We have an example image that you create from this tutorial. And basically what it does is it installs the BXARM tools into the containerized image. And we also have a set of scripts that set up an alias. And so what that alias does is that anytime you call IARBuild or some of the build tools like ICC-ARM, iLink-ARM, instead of going to the ones inside of BXARM, it actually calls the one that's inside of the Docker container. So it lets Docker decide how to spin up and how many different configurations it wants to do in order to be able to build that code as quickly as possible. And as I mentioned, it is kind of a vanilla implementation that we have on GitHub, but it's to show you how to set it up, and then you can completely customize it to your build needs from there. So it's a very cool thing. But in addition to that Docker thing on GitHub, we also have a Jenkins implementation on there and a few other things as well. And we're going to continue to add different things to that GitHub. So be sure and bookmark the GitHub/IAR systems because we're going to continue to add extra stuff to that. So let's take a look at what happens when we're trying to move from an IAR embedded workbench into a continuous integration flow, because some people are a little bit confused about, well, how do I go from the build process that I've been using where I just build everything using the embedded workbench for ARM on my machine, and it just basically, I do the download and debug, and when I'm satisfied, I just do a check-in to my source code control system, and then we just go from there. So how do I move into a continuous integration workflow? Well, this is where most people are. They're just building with the embedded workbench. They build the code. It produces a firmware output that basically goes into your embedded system. But what we're going to do when we move into a continuous integration flow is that whenever we make changes to code, it goes into what's called the development branch. In other words, we're working on some code, but we're not sure we really want to push that out to production just yet. So it goes into a development branch in GitLab. Now, GitLab will notify Jenkins that, hey, somebody has done a code commit, and you probably want to look at this. And so what Jenkins will do is once it knows that there's a change, it's going to do a clone. In other words, it's going to copy that latest commit to Jenkins, and then it's going to begin its automated tests. So the first thing that Jenkins will do before it can do the automated tests is it's going to contact Docker and say, hey, I need you to build this code for me and let me know if there are any errors, because building is the first test that any build system does, including when you're using just the embedded workbench for ARM. So Docker kicks off the IARBuild tools, and if they build successfully, what it's going to do is it's going to notify Jenkins, and then Jenkins is going to start running its automated tests to see does it comply with the specifications and all the automated testing that the software quality assurance people have put together. So if those tests pass, then what it will do is it's going to push that code out to the production branch, which means this is the part that actually goes out to embedded devices out into the field. And so if it goes into the production branch, it winds up getting built again, probably through a Docker container as well. And then that gets pushed out to the embedded system. And so that's what we mean when we talk about continuous integration and continuous delivery. So the continuous integration part is every time you do a commit, there's a series of automatic building and automatic testing that gets done. And then the continuous deployment is if it passes all of those tests, if you push it out automatically to the embedded system, then that's the continuous delivery. So this is what some customers are using, not necessarily all. Some Sorry about that. My microphone cut out there. So this is what some customers are using. And it's not every single customer, because some customers who are in functional safety settings like to be a little bit more deliberate with the testing that they do, so they're not comfortable with doing the full continuous delivery. But it gives you a higher quality code base and quicker feedback on any potential issues that are inside your code. We published a white paper a few months ago that talked about the feedback that developers get is just as important, or the timing that they get in which they get that feedback is just as important as the feedback that they get. Because if the developer doesn't see the feedback almost immediately when they're compiling their code, they have this higher tendency to just ignore it or treat it as, well, that's not really a serious warning. Whereas if they get the feedback instantaneously or almost instantaneously, they tend to treat those types of issues as much more serious. But if it's something that happens where the testing is done overnight and they don't get the feedback till the next morning, there's kind of that survivor effect that takes place where people say, well, this really isn't a serious issue. Yeah, that's just being picky. But if you get that instant feedback, they tend to treat it much more seriously. And it was a pretty cool paper we cited from ACM that came from Google. So it's a pretty neat thing. Moving along, there's some alternative ways that you can do building. There is CMake as well as Ninja. So CMake is an open source cross-platform system that manages your build process. So why would you use CMake versus IARBuild? One of the reasons that customers might do that is because they may also be developing a desktop application or something completely different, where CMake has a make process for that desktop process or whatever other things that they're doing. So by using CMake instead of IARBuild, it kind of consolidates the number of build systems that they have. So it makes it a little bit easier to contain and control. So that's why sometimes customers prefer to use CMake, because it makes it easier to learn one build system as opposed to maintaining multiple build systems. So we do support CMake. CMake is a higher level process, and it can invoke a build process like Ninja. Ninja is extremely popular these days. And it is a build system that's focused primarily on speed and getting that build to happen as quickly as possible. So it is designed, as I mentioned, to have its files and build processes spawned from a higher level build system like CMake. The build files are human readable, but they're not exactly obvious how you would create them from a text editor. So you can figure out what's going on by reading them, but you probably would have a hard time coming up with that flow on your own. It has very limited syntax, very simple build rules, but it produces faster builds because it doesn't have to do a whole lot of parsing on these build files. It also works on Unix-like systems and Windows. It defaults to run commands in parallel. So if you have multiple cores on your machine, it will default to run those things simultaneously. So next up, a CMake example with build tools for Linux. This kind of just shows you the command line invocation for this and how CMake would work. So if you want to use CMake in your build process, you can certainly do that as well. What I'm going to do is show you some build process in practice. I noticed that I've talked a little bit long, so I may not have time to actually do the screen share and show you these things live, but let me run through some slides that at least show you what this looks like. And if I have a little bit of time, I'll do the screen share. If not, you can always contact us and we can do a one-on-one demonstration and let you ask questions and take it for a test drive. This first screen shows the Debian installation package and how you install that deb package. For those of you who are familiar with Linux, you're probably very familiar with the Debian package. It's a very mature way of distributing code. It just comes in one source package, and you can either use dpackage or apt-get install in order to be able to install that package. So there's some pretty cool package managers that come in Ubuntu and Debian-based distributions that allow you to be able to do that. We do typically distribute it in Debian format. If need be, we could probably get it to you in a tarball as well. So it depends on what you need in your build system. Here we're using the tree command, which is an optional package for you to install on Linux that kind of shows you the structure of the folder and how things sit inside of the BX-ARM toolchain. As you'll notice, if you're familiar with the embedded workbench for ARM, it directly mirrors the folder structure of the embedded workbench for ARM. So what this means is that when you pull your code into BX-ARM in order to be able to build, whether it be on the BX-ARM system or on a Dockerized container, you're not going to get any nasty surprises because the directories are different or file names are different, because it's exactly the same. So it makes life much, much easier. Here is where we're invoking an IARBuild with the EWP project. As you can see, it's relatively simple and straightforward. You just call IARBuild with the project name and the build configuration, and you're done. And one of the options that you can do is you can also do a parallelized build. So at the end of that option, what I can do is put in a dash parallel and then give it the number of processes. So it's dash parallel space 4 or 8 or 2 or whatever you want it to be. So that will parallelize the build process. And that works with the Dockerized containers as well. So it works incredibly well. Here is where we invoke the code analysis with IARBuild. So as we mentioned previously, it's basically the same type of calling convention. One of the options in between the project and the build configuration is we give it that dash cstat underscore analyze. So that kicks off a cstat analysis. And as I mentioned, the cstat analysis will create that SQLite database, but in this command line invocation, what we've also done is we've generated an HTML output, so it's a little bit more human readable and easy to see. And so what the analysis report looks like is this. This is the very top part of the analysis report. If you scroll down, it shows you the number of system-wide checks that you enabled, so you see all the different rules. You get the list of messages that were produced by the files, and it has a nice clickable link. So if you click on it, it will show you the file, and it has all the different violations that file had. So this is that instantaneous feedback that we were talking about that helps developers be able to fix those problems much more quickly while they're in the zone of coding, rather than, okay, well, I've slept overnight and I can't really remember what I was thinking when I wrote that code. And I see that I only have a couple of minutes left, so I'm probably not going to have time for the live screen share. But in summary, the embedded workbench has very powerful command line tools for building embedded applications. And it's perfectly suited for continuous integration and indeed continuous delivery systems. It's supported by IARBuild as well as CMake. You can also roll your own build system too if you want to do that, because most build systems are based on the command line invocation of the build tools anyway. So the syntax is there. They're eminently callable as well, so that makes it fairly easy. And our build tools enable automated builds on Linux hosts as well. And if you want to try it out, you can also try it out on Windows 10 subsystem for Linux. So it works quite well there too. So in conclusion, thank you so much for attending this. If you have questions, feel free to email us at fae@iar.com. You can also reach out to your local IAR office. We have 12 offices located around the globe, including 3 in the United States. So if you want to reach out to your local IAR office, we'd be more than happy to talk to you about this, give you a personalized demonstration, let you take it on a test drive through the computer, see how things work and how the overall flow is. So thank you so much for attending this, and I hope you have a really great ARM Dev Summit and a really great day. Thanks.